Hello everyone,
Mhm.
thank you for joining us for this new Platform Zero webinar. So in case you have missed the previous ones, all of them are available on our website, which I will send the link in the chat in a few moments. And so this one is the third webinar, which focuses on big data and predictive maintenance in photovoltaics industries, sorry. And so I will let my colleague Paul introduce it to you.
Yes, thank you very much for the introduction. I will give an overview about some of the work we did inside the scope of the Platform Zero project. I am from RISC Software GmbH, and we are within the project mostly working on the topics of big data, data integration, and also in general, we do some work on predictive maintenance and AI related tasks. Within the Platform Zero project, just set the scene, the focus is on ensuring that the production of solar cells of different types is done properly. That means that we want to reduce micro defects through steering the production process accordingly. There are a few products which may come out of such a production, like solar powered robot lawn mowers, or basically controlled e-ink price denominations, and solar integration for blinds and related topics. In general, in Platform Zero, what we want to do is we have a production line where the solar cells are being produced, going through a series of steps. And we want to integrate, or actually, we are just in the process of deploying sensor stations to the production lines. These sensor stations have been custom built with custom sensors for the project, and the data being collected there during the production process will then be collected in a data infrastructure and then integrated and used for machine learning training. And these machine learning models are then used to determine whether a solar cell is expected to be okay or not okay, depending on the applied production parameters. To just give you an impression of how that could look like in general, we have multiple types of defects that can occur, like, for example, on a CHES type solar cell that's shown here on the left. And then we have, for example, a view of the sensor station, or at least that's, I think, an older version, which is basically showing how that would look like on a hardware level. And then there are some setups how the sensors can basically track these errors. And there is some sensor equipment connected to an analysis machine in the lab that's at the project partner UPO. They are focused also on doing characterization based on sensor data. The overall data flow for the project is more or less, we have a production line. There we have the sensor stations which are collecting the data from or producing the data from different types of sensors, like Raman or photoluminescence, for example. And this data is then stored either in a file system in a specific format. For example, you could use CSV or any other format to store it there, or you can put it directly into a database where it is structured and stored in a table-like format. And then we are within the project, we are also using that infrastructure for doing data pre-processing. So the data pre-processing is mostly focused on extracting the KPI data, so the key performance indicators, from the raw data. So what we want to do there is to determine which part of the collected sensor data is really relevant for the performance of the resulting solar cell. So the data pre-processing is really more about extracting the relevant data for forecasting the performance of the produced solar cell. When we have extracted that KPI data during data pre-processing, we can do AI model training. So we are training a machine learning model, which is then be used for inference. Basically, this AI model can then be deployed at the production line to directly give an indication about the expected quality of the expected performance of the solar cell in terms of how much of the sunlight can be turned into actual electricity. What we also see here is the data management platform is running on top of Kubernetes, which is a clustered version of containerization. So we really put all of our code for the data pre-processing as well as for the AI model training into containers. That means that basically wrapping everything together, the executable, the libraries, and so to be really flexible in terms of the execution environment. And that also means that we can move these containers then also to a place next to the production line to do the AI inference there. I also want to talk a little bit more about general challenges in data processing, because this is kind of the topic that we are working in our group in general. So we are facing some challenges in terms of, for example, different file formats. They are changing. For example, if some partners are saying, okay, we have some new data, we need to change the table where the data is stored, there will be some new columns. Then there are issues with date formats, time formats. Yeah, there can be different time zones, for example. Then we have file name inconsistencies. Then we have different sampling rates, which we might get from different sensors. And sometimes the sensor data is just plain wrong. So we also need to detect if there are errors in the sensor, if the data that's delivered is consistent. Some examples to show some actual practical examples what that error or inconsistency could mean. If you see such a date like on the screen now, like 04/05/2020, you don't know whether you start with the month or with the day, because depending on the region in the US, it's typically starting with month and then day and then year. In Europe, you start with the day and then the month. So without additional information, you just don't know which is which. Same is here. Okay, this is a little bit more structured. Of course, here you can say that's a more sensible way to represent a date. You start with a year, then you can obviously infer, hopefully, that the month and the day is next, and then you have a time. But you're still missing a time zone, so you don't know which time zone you're talking about. Ideally, when you're processing sensor data, you would be using UTC, so kind of a unified time zone, and you don't want to have local time zones there, because this introduces inconsistencies. A good example for this is the daylight saving time. So you have, for example, sensor data recordings in these areas, and these are typically exactly the time window of 1 hour, where the time is actually the hours either skipped or duplicated if you're using local time with daylight saving time. So this can get really crazy if you are not using UTC. So you have to be really, you have to be aware of these issues ideally. Otherwise, the fixing these issues later on gets quite complicated. Another example is you get sensor data and you have to check if the data is plausible. what you can see here is a typical CSV file, which basically gives you like a table with different columns with timestamps and temperatures for a heater, boiler. So that's basically about a steam engine. But what we can see here in the column for power dynamo, so that's really about power. So that shouldn't be a negative value. But what we can see here is in the actual sensor data, there is minus 0.019. So that basically means that should be zero, but the sensor isn't that precise and delivers a negative value. So ideally, you have the domain knowledge. You have to apply the domain knowledge to infer that this should actually be zero. And this is also a matter of data cleaning to just fix these errors. Or if you have enough data and you don't care about the specific entries, you can also remove that lines altogether. Another example, it's basically you're getting different measurement data from different sources. So you have different types of timestamps with different time zones. You have, for example, measured data with different units. You can have PSI, millibar, Celsius, Kelvin, meters per second, or kilometers per hour, or yeah, and then you have to merge it together into one table, and then you ideally need to unify the data. And quite often you're also missing some entries because the data just isn't there. So you have to be aware of these issues to really work with different types of sensor data properly. Another issue which is quite common is thinking about data formats, file formats, and for example, there are many different criteria which are relevant to the what file format you want to use. There are different, okay, for example, we have a pickle file format. That's a file format for storing a machine learning model. We have Parquet, that's quite a common format for saving structured data, tabular data. Basically, it also includes already information about the schema, so you know what data types are in there. And then you have other data types like HDF5, which is also a format for storing structured binary data. But you can see there's a large difference in terms of read speed, for example. So if read speed is a relevant performance metric, then you have to really check what type of data file storage do I want to use. So there are many different design criteria for really setting up such a system to properly work. For example, if you're running on a production line and there the solar cells are moving through the production line, you have only a limited time window where you can basically check the quality of the data of the solar cell, and that also means that you have to consider such performance issues as well to really properly set the whole thing up. Which is going in a quite similar direction is the question of where do I actually want to run my code, my inference, my data integration, my data preparation. We are using different technologies also within the Platform Zero project. We started with a small Kubernetes cluster, which is basically a distributed method for running containers. So we kind of wrap everything together we need for a task into an isolated environment, all the libraries packaged together that's needed there. And then we run it on a distributed environment. But for example, if you in a different project, also a European research project, we had the issue that we get sensor data in a size about 7 terabytes. And this is really a thing which is running in parallel. If you really want to do the analysis properly, it's running for months if you like. And if you want to get your output within basically a few days, you really have to think how to speed it up, how to parallelize it. So that's really a crucial aspect to think how to execute in parallel, how to distribute the data, how to manage the parallel executions. There are a lot of libraries which can support you there, but you need to have a good overview about the general understanding of the issues that need to be addressed there. Yeah, that's also a quite scary slide. I'm ready to admit this. So I just wanted to show you that on one slide. That's a Python code which is doing feature extractions, and this is also for the parallel execution, like I have been showing before. So you set up a parallel environment with a local cluster there, and this is distributing the task using task. That's a Python framework which can be used for parallel execution. And yeah, we are running these on a kind of a big Docker host for now, where we have lots of RAM and CPUs, and using local threading. You can also distribute this across different nodes. And in this setup, we are using the file level for parallelization. That means that you have a large number of input files and you can run different threads in parallel and actually processing these files in parallel to speed up the feature extraction. So when we compare this to Platform Zero, this would basically be the KPI extraction, but on a scale where parallel execution is mandatory to finish that task in a reasonable time frame. Okay, so now we are back in Platform Zero. We have a lot of different types of sensor data that are collected there. As I already mentioned shortly, we have different sensors shown at the left, which are collecting different time series data, wavelength, energy, Raman spectroscopy, and also we have a lot of images which are collected by cameras. And we really need to pre-process that data and extract the KPIs as described before. Yeah. In Platform Zero, the general idea is that solar cell is moving through the production line, and then it gets more and more data gets merged together. So you do a feature extraction, and the features are basically covering more and more of the process. So on the left side, you have just passed process step 1, so there is really a lot of information still there. So and what you do, you basically collect all the relevant information from each process step and you reduce it by extracting the KPIs. And in the end, the KPIs are representing the influence of all of the process steps before, because you are measuring the behavior of the solar cell. You can use different sensors for this, like shown before. And in the end, you extract the relevant KPIs for the actual sensor measurements at the end of the production line. But ideally, you can also use this setup to get that information about the expected quality of the expected efficiency of the solar cell also earlier. So the machine learning model that we are training in Platform Zero is using these KPIs as input, and the output of the model is whether this solar cell is good, whether it's efficient. So there are quality criteria which have to be fulfilled. To say, for example, we have a quantum efficiency saying which percentage of the inbound energy from the sun is converted into electrical energy. This can be such a quality criteria. And based on this, we can estimate this based on the available sensor data at a specific stage. Then we can say, okay, this solar cell is expected to be good. you can also use this information. For example, if you already determine after process step 1 or 2 that there are already some obvious flaws, that the prediction is really strongly pointing into a not good direction, then you could possibly skip the further process steps to save on resources there. Yeah, I've been talking quite a bit about the KPI extraction and, of course, also on the AI model training that's also to be done there. What we have been doing, we have putting this into different containers. So, and then the question is when you're executing all of these things. So there are methods like workflow management systems. We have been using Airflow in this case. So we have been defining these jobs. Basically, you can imagine it that way, that the sensors are producing data. This data is stored somewhere as files. And then the Airflow job is basically looking if there are some files there, if there are some new files. And if this is the case, the KPI extraction is triggered automatically. So you basically don't need to monitor it manually, and it also isn't needed to be triggered on a time schedule. So you're typically not running it every hour or something like this, but you are just checking, okay, there is new data, so I need to run the KPI extraction on the raw data. This is, for example, as you can see here, this image to KPI calculator that's extracting KPI information from image data that has been produced. And then there's a second workflow, which is doing the ML training. So this is basically taking the output of the first job, taking the KPI data and doing a ML model training. So the overall data flow is for platform 0 is we get the sensor data, and this is then stored into the timescale DB. That's a specific database for time series. It's basically an SQL database still. It's a Postgres extension. That means that we are specifically prepared for storing time series. Like, for example, the platform 0 sensors are producing. So you have some sensor values that are changing over time. These are stored in the timescale database, and from there, the model training can work with the KPIs. In the setup of the Platform Zero project, it was decided that the KPI extraction should mostly be done by the sensor partners themselves. So these are the project partners who build the sensors, who have the expertise, how the sensors are working, and what data they are producing. So the idea was to have them set up a sensor which is delivering already the extracted KPI data, and a master server is then collecting this data and storing it into the timescale database. So the database is really the central point here, because it contains all the data that's needed for the model training. There we are training the machine learning models, which are and all of this stuff at the time scale as well as the model training is running on top of the Kubernetes cluster. We also have the option to upload the KPI files directly there or some raw data, and we can also run the KPI extraction there. So that's an additional optional path that we can take if the project partners rather deliver raw data. Then we can also run the KPI extraction on the Kubernetes central infrastructure. Out of the model training, there is this pickle file coming out. This is basically the model file, and this can be then picked up and deployed together with the inference at the production line. We are just now in the process of setting that up. So basically, setting up the model training, and then additionally also implementing the inference side and deploying this to the production lines. The data platform itself that we set up mostly during the first year of the project is, of course, running on top of Kubernetes, as I already mentioned. Here we have the timescale database as shown before, and also an SFTP server that's a typical classical protocol for file transfer. So you can upload files of any type that can then trigger the KPI extraction. You can upload images there. You can upload raw KPI files. And yeah, the files are stored on the block storage. So that means that's an actual file storage that's accessible through the FTP service. And then there is the timescale database. That's the relational database with the time series extension, which will then contain the KPIs. We already did some work there, basically on KPI extraction and putting it into the timescale database, but we still need to fully integrate all these pieces together. This is our example of how we transformed raw sensor data into the KPI formats. This is an Excel sheet that we received from project partner UPO. This is basically, they have provided raw measurement data, which is containing the efficiency which is basically depending on the wavelength of the incident light. So this is basically it's an integration about along different wavelengths, and you compute for example, the efficiency of the solar cells. So that's the EQE value, for example. And what you do there, this is the KPI extraction. So you get the raw data that's shown here in this towards the top right. That's this DOT files, which are just saying, okay, this is the wavelength and this is the measured value corresponding to the wavelength. And then you do an integration of that. You compute the corresponding current which is coming out of this. So the Excel files contains all the formulas. This is what has been used as a template for us to basically compute the output current, in this case, from the wavelengths that have been measured. And what you can also see here is the CSV format that's in the background here. That's the actual representation here. This is the format for storing the KPI files that we have agreed on in the project. So this is the format that we use for actually storing the KPIs, the KPI data also in the database, which is then used for the model training. As project partners RISC, we have also published some work there in an open access journal. That's for the Open Research Europe. Basically, that's focused on the data preparation. So we have done multiple use cases, and exactly this KPI extraction from the data from UPO we have used as a use case to show that we can use configuration files to just run such data preparation jobs. So the idea here is that you don't have to re-implement this data preparation code every time you get slightly different data, but you can identify different steps there, like, for example, reading from a specific file format or doing resampling, adding new entries, doing interpolation. So these are steps that are reoccurring across different use cases. And the idea is to have prepared code for that and that you just write into a configuration file how you want to combine these prepared modules into your full workflow for the KPI data extraction. Yeah, this is kind of putting everything together. We have this automated data extraction based on the configuration files, which is producing a CSV, and this is running as an Airflow pipeline. So this is an automated job which is running on our infrastructure, reading the raw data and automatically extracting the KPI data and writing it into the database so that the ML model training job can be executed. Okay, so this was an overview about the project, about the Platform Zero project. And now I also want to give you a short overview about some work we did in a different European project, which kind of ran in parallel with the Platform Zero project. That's the manufacturing project that concluded by the end of last year. So it was a 3-year project which was focused on a digital twin for metal part production. So mostly casting and welding. And we also did some stuff in terms of data pre-processing there, as well as doing some data science work. So really forecasting product quality based on the process parameters that have been observed there. So it's kind of similar to the Platform Zero project. So the general idea is in both projects, you collect process data, you collect sensor data, you train a model, and this model will tell you, based on the measured parameters, on the measured sensor data, how good your product is expected to be based on defined quality criteria. What we want to do in manufacturing is, there are also multiple steps, of course. So you get the raw data out of the manufacturing process, which is basically turning the materials into the product, obviously. And then you also have some stuff like the strength test. That's a quality check that's done after the fact, after the product has been produced. And this is basically the feedback loop for the forecasting of the product quality. So in the end, you want to have a machine learning model which is fed the process parameters, also the material. And then the model should basically tell you, is the weld seam expected to be okay, or how strong is it, or are there some issues with the casted parts? So you want to forecast this relation, but you also need the measured values that you get from the strength test, from the actual measurement of the produced part, to really check and to calibrate the model. So you have really a ground truth against which you can check the quality of your machine learning model. What we can see here is a welding process that has been used as a use case in the manufacturing project. What you can see here is there are multiple metal parts which have been welded together. There is a camera system, so you can see an image of the weld seam, and then you can check the quality of the weld seam. Also, there are cuts through the welds, which are done on an irregular basis to check really the quality of the weld seam. What you can see here, how the welding equipment is moving over the workpiece. The loop is basically you're getting the process parameters. These process parameters are used to configuring the manufacturing process. Then you run that process. Then you do the quality inspection, And based on the data from the quality inspection, you can feed that back into the process parameters. So you use a digital twin, you use the machine learning for actually tuning and calibrating your production process so that you basically reduce the amount of scrap. So you obviously want to reduce the number of parts that you need to throw away. And you also want to reduce the amount of quality inspection that you have to do because all of this is costly. The products that we were targeting there is, for example, battery trays for electric vehicles, improving the quality analysis, and yeah, also doing a root cause analysis. So we really want to know what is the reason for a defect, what is the reason for a weld seam not being done properly, and of course provide decision support for automated improvement of the welding process parameters. In the overall view of the project, we were collecting different types of data, like welding process data, that's mostly time series with different frequencies. Robot path data, it's also time series. And then we were really matching together different data streams, for example, based on the robot positions along axis, or we were also using the timestamps for merging. And we also did a lot of resampling because the different sensors produced a different sampling rate in terms of the data produced. There's also video data, which is then merged together. You also really have to figure out how to match these different types of data, like, for example, the energy that's coming into the system, and you really want to match it up with the weld seam. So to say, okay, at which time the weld robot was exactly above this point, and so that you can really see what's the effect of this amount of welding current on the specific location of the weld seam where this was applied. The traceability data is really also quality data from a manual inspection that's also merged here. Yeah. As I already mentioned, we had different types of data there. We have high frequency and low frequency welding data. So basically up to 10 kilohertz for the high frequency, low frequencies was 1 kilohertz. So we did a resampling to upsample the low frequency to the high frequency. And then we kind of want to merge all these data streams together and match them up properly. Yeah. The The target is, of course, the detection of deviations and anomalies based on the welding process signals. So you get information like the current, you know what energy is going into the weld process, you know the voltage, you know the current, and then you match that up with the specific location of the weld seam. You know what's okay, what's not okay. You can see the visual comparison here on the right side. So when you have a not okay weld seam, where you have parts of the weld seam which are lacking, so to say, then you can say, okay, it's relevant for me to know uh, what was the voltage, what was the current that really affected this. And you're also using that quality information that you get from the manual inspection, from the camera inspection as well, to do the model training. So you get this ground truth, you know, when I put in this amount of voltage, amount of current, I get exactly that output. And so the model is trained, the machine learning model is trained to really learn about these correlations. Then you can say, okay, I need a consistent voltage and a consistent current of this amount to really reduce these errors. Yeah. The idea was to use the machine learning model to find these defects, and we want to really pre-select weld seams for further inspection by downstream quality inspection. That means that downstream quality inspection is a manual inspection, which means it's time and cost. Yeah, it takes some time. It takes manual labor. So you really want to send the right pieces for manual inspection. So what you're doing, you basically use this machine learning model to see, okay, I know this, the currency or the current and the voltage curves are fed into the machine learning model, and the machine learning model basically predicts the quality of the weld seam. And when the quality of the weld seam is expected, or the model is telling you, okay, there may be an issue, this would be a good candidate to check in manual inspection. If the machine learning model is saying, okay, everything should be fine, you normally don't need to check this one. So you're using the machine learning there to kind of steer your quality inspection towards pieces which are highly uh, probable to be, to have issues. So you really want to spend your workforce, your energy in the quality inspection on the right pieces. So this is the idea here. Yes, this is basically the matching between the prediction and the inspection quality for different seam numbers. So if you do weld seams, the data that we got, all that the weld seams were structured in a different way. So what you can see here is, okay, there were a lot of okay weld seams, obviously, because if you're producing welded parts, you basically want good parts. So this is also an issue in general with the machine learning model training, because you also want bad parts, because if the model doesn't see these bad parts in training, it also isn't really able to learn the parameters or the input criteria which lead to such bad parts. So this is one of the main issues here. But we can see here that in general, the inspection and the prediction match up quite well. Yeah, another thing, the overall analysis of the welding process. So at first, that's kind of the workflow again. First, we do a data pre-processing, and feature engineering. Data pre-processing is exactly what I mentioned before. We have different sensor streams that are matched together. You basically, for example, the welding signals in different channels start at slightly different times, and then you have to shift the signals along the x-axis a little bit to really match up the timestamps. Then you have to resample them, so really to align all the different signals properly. And then you can visualize the feature space. So the feature space is, you have a lot of sensor data and you want to get an information, what type of sensor data, what type of sensor, what type of information is really relevant to the quality that I'm interested in. So if you have a machine learning model which is getting a lot of sensor input, so for example, if you have here, you have feed speed, you know how fast the workpiece is going through the welding process. You have, of course, the current, you have the voltage, and you want to know which of the data streams is mostly relevant for my outcome that I'm interested in. So that also means that you can reduce your raw data and also only train your model on less data. That speeds up the model training process. So that's highly beneficial in terms of the overall performance of the process. What you can do here is to see, okay, using clustering methods. So basically, see what sensor channels are behaving in a similar manner. And what you can also here see under explainable AI, so that's the insight which can be derived in a combination from the training process as well as the inference later on to see what actual values are contributing to the model in the most, which actual channels, which values are contributing to the model most. These are the sharp values. They really give you an impression of which sensor values contribute most to the model and to the model results. Okay, this was basically an overview about the work that we did in these two projects. It was a rather brief overview to mostly give you an impression what are the relevant aspects that we are facing, that we are working with here, both in terms of the data preparation, data integration, as well as the AI work, feature engineering, and doing machine learning model training and forecasting of product quality based on machine learning. And some takeaway messages for this talk is, having data is not enough to improve products and processes. It's a necessary prerequisite, but it's not good enough by itself. Typically, you either don't have enough data, or you have the wrong data, or the data quality is lacking, or you are covering only the same cases. So, for example, you only have good cases for your product, which is very nice for your bottom line if you're producing these parts, but it's very bad for actually training a prediction model for product quality. Big data is challenging. That's a very short sentence for a large area, which may cover a few hours of presentation by itself. I rather shortly describe this. So you have different types of data quality, different data formats, and you also need to think how to store the data, how to model the data to really retrieve your results quickly. So that is quite a large field there. Unlabeled and unsynchronized data makes things even more challenging because these you have to have properly synchronized data from different data streams to really do proper feature engineering, to do proper machine learning. Data fusion and data reduction are critical pre-processing steps. So, as you have seen, you have getting data from different sources, you have different sampling rates, you really need to match that up. Quite often you have null values, which because if you're collecting from different sources with different sampling rates, then you merge the data together. And you have to think how to fill up that null values. That also depends on your domain. So you need a domain expert to tell you, okay, you can skip these values, you can interpolate them. So that's also not only a matter of data engineering and data science, but also a lot of domain knowledge is acquired there. The good thing is that in-process models and data, that's kind of called a digital twin, can limit the need of destructive testing and allow for online process steering. So that's really the ideal scenario. You basically are able to get an online information, an online immediate feedback to see, okay, something is going wrong, you need to change a process parameter. And this is really enabled by the fact that the inference, so the actual usage of the pre-trained machine learning model, is way faster than the training process itself. And also, as I already mentioned, input from domain experts are essential during data pre-processing and feature engineering, as well as model interpretation to ensure meaningful and accurate machine learning results. So here at our company, we have a lot of expertise on data preparation, data handling, machine learning, but we are not domain experts. We are not experts in welding, in casting, and also not on solar cells. So we really need the feedback from the domain experts. And for example, for Platform Zero, it worked quite well. It honestly took me some time to really get into that topic, but that's the whole collaboration, and it's really a nice experience. That's also what I like quite a lot about these collaborative projects. So I think that's a good conclusion from my side, and I want to close the presentation on this. Yeah, if there are questions, of course, I'm happy to answer these.